In this video, we're going to find the directional derivative of this function given by the square root of x times y at the point 1, 4. And in the direction indicated by the figure here, I have the x and y coordinate system, and I'm indicating the direction that you would go in if you were to take an angle of pi over 3 radians and walk along the ray that that angle determines. So the first thing that we're going to need is the gradient of f in order to calculate this directional derivative. So f is x times y to the 1/2 power, so just writing it as a power. And we're going to need its partial derivatives to get the rate of change as I vary x, and I'll do the power rule. So I'll bring down the power, go down a degree. I'll leave the inside alone, and then the chain rule requires me to multiply by the derivative with respect to x of x times y. That will give me a factor of y. Rewriting this expression, it's going to be y over 2 times the square root of x times y. My function is very symmetric. If I interchanged x and y, I wouldn't notice the difference, and therefore their partial derivatives should have symmetric answers, and we can pretty much avoid the calculation here and jump right to the fact that the derivative with respect to y will be x now over 2 times square root of xy. So abstractly, my gradient vector, the gradient of f, is the symbolic vector whose components are the partial derivatives that we just computed. But we want the derivative in at a particular point, so I'm going to evaluate at x and y equal to 1 and 4 respectively. So we'll evaluate at 1, 4. And we'll plug in those values for x and y into both of our derivatives. And simplifying, I get 1 and 1/4 for the gradient vector. The next thing that we need is the direction that we want to go in. We've only indicated it descriptively here. We need a unit vector, let's call it u, which is pointing in this direction here. Well, we can use the standard trigonometric functions to get such a vector. The x component should be the cosine of pi over 3, and the y component should be the sine of pi over 3. That will be a unit vector, and indeed will have the orientation that we want. Cosine of pi over 3 is 1/2, and sine of pi over 3 is root 3 over 2. So there's our unit vector in the direction that we want this derivative. Now we can compute the directional derivative. We write this as d sub u of f, and you read this as the directional derivative of f in the direction of u, and then we're going to evaluate it at the point 1, 4, so we're getting it at this point p. This will be a scalar quantity, and we get it by taking the dot product of the gradient at our point with our directional vector u. And now this is a straightforward calculation. Here's my gradient, and we'll dot it with u, and we'll get a scalar 1 times 1/2 plus square root of 3 over 8 will be the value of this directional derivative. And if you go to a calculator, get an estimate of that, it turns out to be about 0.716. Let's spend one moment here just interpreting this answer, at least trying to get some perspective of what it tells us. Here's some plots that I've made here. This first one is the surface given by z equal to the square root of x, y. So I'm plotting my function here in 3 dimensions. Just in general, as I move my x and y coordinate out this way, I kind of see the z coordinate increase. So if I'm taking a directional derivative somewhat in this direction, I should expect it to be some positive amount that indicates the rate at which I'm climbing on this surface. Each one of these curves on the surface indicates a constant height, a level height. Underneath, I've plotted a contour plot. I'm plotting the level curves of the surface, so I'm looking to see where my function f is staying constant. If I walk along one of these level curves, my function doesn't change. And then the computer is also indicating some color coding here that's indicating the value of the function. So I would assume here that near the origin, we're close to being 0. So we can see the value of the function is small here, and it's indicating that with this cool color here. and as I move away from the origin, it seems to get warmer, indicating the rise in the vertical direction. I've found two vectors. The first one was the gradient. The gradient was the vector 1, 1/4, and that is this vector right here. So there's my point, and there's the gradient vector drawn at my point. The other vector we found was u, indicating our direction that we want to calculate the directional derivative, and that's that vector there. You can see that the gradient vector is normal to the level curve because it indicates the direction of most rapid increase, and so you want to move across those level curves as rapidly as possible to see that increase. My directional vector is not quite normal, so it's not going to be increasing as rapidly in this direction. And in fact, what we would expect from this answer right here is that if I walk 1 unit in the direction of u, that I would expect it to climb about 0.716 in the vertical direction. You can compare that to the length of the gradient. The gradient of f is also a directional derivative. It will be the derivative in the direction of the gradient. And if we find the length of the gradient by calculating its length, we get about 1.031, and you can see that this number here is larger than this number here. If I was to walk 1 unit in the direction of the gradient, I would expect it to increase about 1.031 units.